Hey guys, welcome back. We are going to continue on with throttle position sensors in a way. We're going to move on to the throttle body motor control. Now, not every manufacturer is going to operate this the same way. I'm going to be using a GM. Now, these are pretty common for throttle body codes. And sometimes it's the throttle body, sometimes it's the pigtail, sometimes it's the throttle body module on the firewall. So knowing how to scope these can be beneficial to you. Doing some voltage checks and ohming out the harness might get what you need, but sometimes you're gonna have to grab the scope. So we're gonna look at the wiring diagram to see exactly what wires we need to hook up to. Now, being that this is drive-by-wire, it is more than likely gonna have two different throttle position sensors for verification. One is gonna have kind of a weird glitchy dropout signal. That's normal on a GM, or at least a lot of the GMs. And then we're gonna have a motor control of some sort. Now, the motor is not gonna have a positive and negative because this motor is going to be able to be forced to go either direction. Unpowered setting, that throttle body is going to allow enough air in there for this truck to probably sit at 1,000 RPM. The throttle body is activated in a kind of a reverse polarity to close that throttle blade to restrict the airflow to bring that idle down. They do this for numerous reasons. One is if that throttle body fails, if it's sitting at 600 RPM, the vehicle might stall and cause some other issues. It could lead to a crash. If it fails and it drops to 1,000 RPM, then it's normally controllable. The engine's not gonna stall out, it's gonna continue to run. If it's too fast, a lot of the newer GMs will actually shut off some of the injectors, make it run a little bit rough to drop that idle down. It'll do it in a controlled way, so it's not uncontrollable. You know, it'll run rough, but it's not gonna shake you to death, it's not gonna stall. So let's go ahead and jump onto the computer, we'll look at the wiring diagram, and then we'll hook up the lab scope. So I have the wiring diagram pulled up here. Of course, there was 5 pages of wiring diagrams. We're almost to the end. Page 4 of 5, we have the throttle actuator control module, or the TAC module, and then we have the throttle body. We're just gonna go straight to the throttle body. On the GMs, it's pretty easy to just pull back the loom a little bit. All the wires are exposed. You can back probe or pierce the wires however you see fit. We have 2 throttle position sensors. They all have their own separate 5-volt reference and ground and our signal wires, and then we have our motor control. So a yellow wire and a brown wire. So that's what I'm gonna hook the lab scope up to. We are gonna use 2 different lab scopes today. I'm going to use the H-Scope app on the Android, and I'm using the HS402 Pro 2-channel lab scope. We'll give that a try, and then I'll show you some additional features that we can use the Picoscope to look at these throttle bodies. After we look at the voltage of the throttle body, I'm going to show you the amperage, because you can see a lot of the big picture with the amperage of what the throttle body is doing. Because when you just look at the waveform, you're like, okay, is it powered? Is it not powered? Is it going forward? Is it going backwards? So if we look at the amperage, we can easily determine if that throttle body is going forward or backwards. Okay, I'm just going to use a piercing probe. I'll seal up the wires later. Got a yellow wire here. And let's find the brown wire. So normally the 2 heavier wires go into the throttle body. The throttle position sensor doesn't really need a heavy wire other than for wire integrity, which obviously didn't work for GM because these wires break all the time anyways. You know, they're not carrying a lot of current on the throttle position wires. They're just, you know, showing voltage. So we're gonna hook my scope ground. I'm not gonna have the engine running for this one, so I'll just hook up to the alternator case. If the engine was running, we might have a little more noise at that location. And we'll just hook these up like so. Now, if I set this up right, then we should be able to see my tablet. I'm not an Android user, so, you know, please forgive me if we have errors. But what I'm gonna do is I'm gonna turn the ignition to the on position, and we're gonna take a look and see what happens on our lab scope. Okay, so we get quite a bit of noise here. It's kind of hard to see what's going on. And let me separate these 2 channels a little bit. Oops. And our power kind of cut off there. Not sure if it was something I did on the screen or if it was the vehicle. So it looks like we're sitting about 3 volts on both channels. So that might be like a self-check mode. You know, it went back into a neutral position. Let me turn the headlights off here. Okay, I'm just messing with the accelerator position. And we get quite a bit of activity happening here. Let me see if I can change our sample rate. I'm still learning this, this scope app, and it may not be a complete square wave. That looks like a pretty good signal there. On one of our leads, the green lead, we are sitting at battery voltage, and every once in a while it drops down to ground. The other one is sitting around, 11.5 volts almost all of the time. Okay, there we go. Now, I'm still learning the cursors and stuff here. On the left side of the screen, we can see that our yellow channel is at 11.57. On the right side, I just put a line across the green where it's at about 11.9. The yellow, it's constantly at battery plus. But the green channel here occasionally is getting pulled to ground. That's going to be our motor control. That's where we would normally see amperage. If they're both at 12 volts, we probably don't have any current flowing. When the green channel drops down, and it's dropping down to almost ground, that's when we're going to have current going through this. Now let me go over to the automotive side, and I don't know if my sample rate is correct here. On this one, you can actually record, and it's going to record it into a buffer, and then you can review it later. So I'm just snapping the throttle a few times, different speeds and whatnot. We'll hit stop, and there we go. So I want to look at this point right here. Here's where I let off on the throttle. We can see that our green channel is, is pulling down to ground. So our green channel is pulling down to ground, is moving the throttle body one direction or keeping it open one way because it's fighting an internal spring there. And then as I let off the throttle body, it wants to close that throttle body fairly quick. It wants to shut down the air. It says, hey, you want to slow down? I want to slow down too. Let's go ahead and turn this thing around. So green now stays at power, and the yellow one gets pulled down to ground. So let's go ahead and hook up a channel where we can monitor amperage. And sometimes the amperage waveform is going to be something that gives us a better picture of what's happening inside of this thing. So I'm going to change my yellow channel to an amp clamp, and I'm just going to throw it around any wire on there. It doesn't matter which one. 20 amp scale should be sufficient. And I say it doesn't matter which one, and the direction doesn't matter because, we're going to see power going both ways. So channel 1, I'm going to change my probe here to a clamp, I think. Okay, so I think I have my settings correct. Not sure. I'm just going to actuate the throttle body a few times. We'll stop recording, take a look at it. This thing lets me zoom way in there, so it looks like a mess at first, but we'll now as I zoom out, you see that green waveform kind of aliasing. There's just too much information in there for it to display. So I'm going to put a cursor at my 0 point. That's pretty close to the 0 mark. So we can see with the amp clamp that I go above and below the 0 point. And if we zoomed into that spot where I go below, we can see, like on my green trace here, my green trace isn't getting pulled down to ground when I have my yellow amperage in the negative. And then as I let off the throttle body, or off the throttle pedal, we see some movement in the green trace, and my amperage goes positive. So that is the amperage actuating that throttle body back and forth. Now I don't know which one is which, open or close, since I wasn't paying attention as I was sweeping the throttle body. But we can see that we get movement in both directions. Now, we're not getting it quite in, that rapid pulsing that we see on the voltage. Now there will be a little bit of noise that mimics it, but because we are running this throttle body at a duty cycle or pulse width modulating it, we're reducing the amperage. We can control the speed at which this opens. We can control at what point it remains at one stationary position. Okay, so let's switch over to the Picoscope. I can just leave all of my leads connected. We'll just plug them into the Picoscope and open up the software on my laptop. We need to add a few channels here. Most of these are going to be, our channel 1 and 2 are going to be 20 volt scale, and then channel C is going to be a custom probe, 20 amp mode on a 60 amp clamp. Should be correct. I don't know what I need for amperage. I think I was less than 5 amps, but we'll throw 5 amps on the screen. Now 5 milliseconds is a lot of speed. I don't really need that. We should be able to zoom in. I have 1 million samples on the screen. So where is my other channel? We got 3 channels here, right? I'm guessing 2 channels are just overlapping. We'll see some movement and we can move stuff around a little bit. We'll just break it up. I'll go actuate the throttle a few times. We'll look at the waveform, see what we get. It looks like, just glancing at this, with no activity on the throttle body, we are running about 3 volts into that throttle body, and I'm betting we're doing that on both wires. It's probably just an integrity check to make sure that we don't have an open circuit. Or it may run 3 volts on one wire and leave the ground ungrounded on the other side and measure the voltage going through, just to make sure that we don't have an intermittent open circuit even when we're not pressing the accelerator pedal. Our other channel, we obviously need to zero our amp clamp, unless that is just a little bit of amperage going through there. Let me do that real quick. It was a zeroing issue. There we go. So our amp clamp zeroed. I'll actuate the accelerator pedal a couple of times, and we'll look at the waveform, and then I'll show you a couple of tricks that you can do with the Picoscope. Let's go ahead and stop this. We'll go back a buffer and zoom in and see what we have. So I understand that my channel labeling isn't the same, or at least my colors are not the same. I have blue and red, and then my amperage is on green this time. I'm going to drop this down here, and I'm going to put a 0 mark on my green channel so we can identify, positive or negative amperage. So there's my 0 point, which I can zoom out a little bit as well. So we can see, when we're sitting stationary at idle, after I actuated the pedal a few times, woke it up, it's trying to pull the idle down, or it might actually be opening it a little bit to get ready for a startup. And then we see some activity in our red channel here, and our amperage goes negative, bounce backs up, positive, goes back negative again, kind of stair steps back, goes positive, negative. So we're seeing the same thing here. Now, what if we didn't have an amp clamp, or we wanted to maybe be able to identify which direction this TAC module is trying to drive this, based off of just the voltage alone. If we were to turn off our voltage, or the amperage channel, so channel C, I'm just going to turn that off. Now, we're going to add a math channel. Now, this is going to, it won't be quite as pretty as the amperage waveform, not quite as smooth, but we'll be able to identify if it's driving it one way or pulling it the other. So I'm just going to go to Tools and Math Channels, and we're just going to do a simple A channel minus B channel to see if that gives us the waveform that I'm looking for. Now it may be inverted from what we may expect to see, but it's going to show us whether it's being driven one way or the other. So if we drop this down here, and I'll throw a zero line on this channel as well. So we can see a clear definition of positive voltage versus negative voltage being applied to this throttle body. You know, one way, the PCM's holding, let's say, wire A at 12 volts, and it's pulsing this one over here, wire B, to ground, pulsing it to ground. And then we're gonna flip-flop those. It's gonna hold this one at 12 volts. It's gonna pulse this other one to ground. That's how we're getting our control. If we do the math channel, we can see that. We can see, okay, it's pulsing it negative, and then it's pulsing it positive. It doesn't actually pulse the positive side. It's just reversing the polarity of the motor and pulling the other side to ground while holding one side to positive. I hope that made sense. It makes sense in my head. You can visually see it. Now I'm going to turn the amperage channel back on, and I may have to invert it for everything to line up properly. I will. Let me I can just change my math channel here. So instead of A minus B, we need B minus A. Simple to create a math channel. We'll do B minus A. We only need to see 20 volts. So negative 20 to positive 20, and we'll hit finish. And we'll turn on B minus A and hit OK. So now that purple channel disappeared. And let me zoom out a little bit here. So now when we look at our waveform, when our math channel is showing positive, our amperage is showing positive. When it's showing below the zero line, showing negative, our amperage is below the zero line as well, and it's showing negative. I'm going to go ahead and make a zero line here. It's really hard to see with the black. We just change that up a little bit. So what I have is I have a 0 point set for my green channel, which is my amperage. I have a 0 point set for my math channel. And I lined them up so we can see when one is below the zero line or above it, that the other one follows suit. So we have purple here that's above the zero line. We have our amperage that's above the zero line. Purple drops down below, our amperage drops down below. We can see right around here we start getting a transition. If we zoomed in on that area, we're probably going to see that that pulse width gets narrower and narrower and narrower. Let's go ahead and look at that. And that's why the amperage is lower. Now this is something that's a little bit harder to plot out. We'd have to do a math channel based off of frequency as well. And it gets a little technical or difficult when we're going positive and negative. But we can see that the pulse width of these lines, when it's getting pulled to ground, it's a little bit wider right here, a little bit wider, and then it starts to get narrower. And it's really narrow right here. These are almost like little pinpricks as our amperage starts going the other direction. And that's how it controls it. It changes the amount of time that it's being pulled, positive or negative. And if it wanted to move it really fast, it could just go full power one direction and really slam it. Now it normally does it just because that throttle body would just hammer itself. But if it was programmed to, then it certainly would. Now I can't really tell you what a normal power range is for these throttle bodies. This one here, we never exceeded 5 amps. It looks like we got to about 4 amps. Some vehicles seem to pull a little bit more. I vaguely remember a Jeep Commander we did a video on, and it was pulling like 12 or 13 or something like that. That's probably why those Chrysler PCMs fail so often. They're a little more power hungry unit. And that's probably why GM, when it implemented this system, went with a standalone controller that communicates over the data network for the throttle body. They didn't have the circuitry built in to the current PCMs that was capable of driving this throttle body and had the extra input for the TPS number two and then the 2 extra inputs for the APPS sensor. They may not have had all of those extra inputs on that PCM. So to get around that, they went with the TAC module. The inputs for the APPS and the throttle body go into that, and then it communicates that to the PCM, relays all the information. Okay, hopefully I covered everything I needed to. We're going on like 15 hours here at the shop, so I'm a little out of it, and I may have missed some things. If I did, comment down below. If it's a big thing, I'll make another video. If it's something we can cover in the live stream, we will do that as well. If you guys are unfamiliar about the live streams, we'll probably go 2 weeks on this one, but it'll be a Saturday night, so like a week and a half by the time this is released to you guys. And we will review any of the waveforms that you guys have performed this test, captured the waveform, uploaded it on Facebook, or emailed it to me, or filled out the Google form. All 3 of those are down below. So if you're not a Facebook user, no fear, you can still submit the waveforms to me, and I will get them and review them on Saturday night. So like I said, questions, comments down below. If you enjoyed the video, give it a thumbs up. If you want to see more videos like this and you want to see me choke over my words and mispronounce stuff and read stuff wrong on a live stream, then subscribe, click the bell. Thanks for watching, and I'll see you next time. And don't forget to seal your wires up when you're done. And turn off the amp clamp.